Hello and welcome to the Advent of Code 2021, day 15. Today we are giving a grid of digits between 1 and 9. And what we are asked to do is essentially to find the path that minimizes the total sum of the digits we found, moving from the top left corner to the bottom right one, moving only in vertical and horizontal. I already copied, and the question is, what is the total risk of this path? So for example, in this case, the sum of these numbers that are highlighted is 40. For this example, I already copied the input for the problem, which is this small example, because that's the sample input, and I've already the scaffolding. So let's start by ingesting this matrix. As is usual, I prefer to use a dictionary to represent it because it makes just faster and easier to do operations like building edges when we do the exploration of the graph. So I iterate over, I create an empty dictionary that I call cells, which is an empty dictionary. Then for every line I have to iterate, so but I also need the index, so I call it row I for the row index, and line in enumerate fr, and then I do the same for the column. So for column index and value in line dot strip, so I ignore the new line at the end of the line. What I do, I have now the row and column, so I simply put them into the cell. So cells of row I and col I is equal to v, but v is a string, actually is a character in this string, a string of only one character, so I take the integer value. And this is the dictionary, so I can already print it to get an idea of what it contains. Python 3, Advent 2021, this is day 15. Okay, not enough values. I didn't enumerate, sorry. Okay, so I got this dictionary, which is simply associating every cell with the corresponding value in the matrix. For example, 98 is 8, 99 is 1, so we can check. This is 8, this is 1, seems correct. Now we pass this dictionary to the part 1 of the problem. How does it work? So this is already, as usual, a graph exploration. So the algorithm will look like this. First, I have a total risk, which is the cost to reach every cell in this matrix. This is basically the result of our algorithm, and it's a dictionary, initially empty. Then I will have an edge, which is the list of nodes that we are about to add, that we are about to explore to get a partial solution. So we're going to create a list of edges, calculate the risk, put it back into total risk, have a new list of edges, and explore the grid like that. So I have the edge, which is what is the initial exploration. What is the initial edge? What is the initial point that I explore? Is the starting point, which is 0, 0. And then here usually I will put the argument for this function is the cells. Here I will put the cells on position 0, 0. But I noticed that the problem here says that the starting position is never entered. So this is not counted. This is a bit weird, I don't know why, but so this is not 0, 0, which is what I will do and will be wrong in this case, but 0. And this is the starting point. So the list of nodes to explore is one single element, which is 0, and total risk is a dictionary. Now I will go through all the elements and follow these steps. So create a new edge, which is an empty dictionary initially. Then for each cell in edge, get the neighbors, so the candidates to be added. For each neighbor, not already in edge or total risk, so something that is completely new that we actually never saw, if that neighbor is in add the neighbor, calculate the risk of that neighbor, add it to new edge. And then after that, if new edge is empty, break the cycle. If it's empty, it means that we found nothing new to add. We completed the exploration. Otherwise, add edge to the total risk and set edge equal to new edge. And this is how we do the exploration. Okay, so now we have the new edge, which is a dictionary of the cells that we're going to add at this iteration, and we have to iterate over all the cells in the edge and get their neighbors. So I iterate over them, so for the cell which is x, y, because it's a tuple of two coordinates, and the risk so far in the edge, so edge.items, I want to get all the neighbors. So what I do is for nx and ny, which are neighbor x and neighbor y, in this list of cells that are at the coordinates that are essentially the neighbors, so x plus 1 and y, x minus 1 and y, x and y plus 1, and then to finish x and y minus 1. I have now all the possible coordinates and neighbors. Notice that these coordinates may also not exist. They can be on the edge, but doesn't matter because now we're going to check. So we say that if an x and y is in cells, so it exists, and also an x and y is not in the edge, so they're not already explored, and also they're not in the total risk, so we didn't explore them neither in the edge that we are expanding now and in the previous iteration, so they're completely new. Fine, we found a valid cell that we can add, so it exists and that was not added at the previous iteration. What we do now is we add it to the new edge, so we say okay, new edge of the cell nx and ny is equal to what? To the risk of the current cell, the one from which we are coming, plus the risk that comes from simply the cell itself. So we're simply calculating the cost incrementally, which is cells at the coordinate nx and y. There is a small problem here, which is that when we calculate the risk of a cell, it's possible that in the same iteration, so from the same edge, we can reach the same cell in two directions. So for example, from the top and from the left, for example. In that case, we may have different costs. So we have to check also that this cell is not already in the new edge. So we say that if nx and y is in new edge, so we already in this very iteration processed it, we do something, otherwise we do this operation. So this is valid if it's not already in the new edge. Otherwise, this will be equivalent to what? To the minimum of the risk of R plus cells, blah blah, and the current value. So we update it only if we found a nicer, better way to reach this cell. Otherwise, we keep the previous value. We don't touch it. So we did this operation. We calculate the risk of the neighbor, which is what we did now. So we are simply implementing the description of the algorithm step by step. If the new edge is empty, break the cycle, which is correct. So if we didn't find anything, there is nothing to explore. We finished processing the problem. So we say that if the len of new edge is equal to 0, then break. And now we have to add the edge to the total risk. So here we have to iterate over the edge, not new edge, but the previous edge, so the one we just completely explored, not the one you are going to create. And we simply add these cells to the total risk. This we can do with a for cycle like this, but we can also do that immediately in this step. So we simply add edge to the total risk. This is something that we have to do in any case. So there is no reason to do that in a separate step. We can do it here. I say that total risk of x, y is equal to the risk of r. And at this point, I do not even need this double check because the edge and total risk are the same. So I simply check that the new value that I'm going to explore is not in total risk, because total risk already includes the risk so far. What I have to do is set edge to new edge. So edge equal new edge. Notice that edge has already been completely incorporated in the total risk, so we can just continue. And then what I do here is I print the result, total risk. So I can now run the code again, and I see that for cell 99 I get 40, which is the result of the problem. So what the problem was asking. What the problem is asking us to do for our real input, which I'm going to download, is much higher, is to get the bottom right cell. So this is the input. I can run and see the result is 707. Now I want to get actually the value. I think the problem mentions the size of our cavern. I do not want to yeah, I think I will have to actually calculate the max of this. So okay, let's take the max x, which is the max of x for x something in cells.keys. So I have to simply calculate the maximum and minimum, the maximum of every coordinate, because I want to get the corner. I know it's this last one, but I do not want to make assumption on the order of the dictionary, because that depends on the implementation. So I do this. I simply get the maximum the maximum for x and y, and then I return not the total risk, but the total risk at position max x and max y. Okay, I print it, but I actually want to return it. And this should be the solution. And in fact, I already tried the problem first because I had to go to get a COVID test because I have to travel, and I already knew that it was 707. So what you're seeing is the edited version of the video to hide the test. Okay, and see you for part 2. Bye.